Hi, sorry to just quickly interrupt. I think mute is still on. We can't hear you online.
I'm very sorry. Now it should be possible to hear. Can you hear?
Yeah, we got you now. That's perfect. Thank you.
Thank you very much.
Okay. My name is Arthemy Kiselev. I'm from Bernoulli Institute for Mathematics, Computer Science, and Artificial Intelligence in Groningen. This is the structural part of the Faculty of Science and Engineering in Groningen. I'm very grateful to the organizers of this seminar, and I'm very grateful to all of you for coming, and I'm very grateful for inviting me this week. I shall give a series of 3 talks, one tonight, another tomorrow, and one on Friday. Each of them can be attended and perceived irrespective of the other two, although the topics are related, of course. But what I tell you tonight is a motivation for our study tomorrow. And today, our main topic of discussion, so the material is graphs, non-directed graphs with finitely many edges and finitely many vertices. And the main message which we as physicists, mathematicians, mathematical physicists profit from this is, suppose that a student comes to you and asks you, Professor, give me natural examples of Lie algebras. Well, 2 examples are immediate, matrices and vector fields. Well, compute matrices RB minus BR, fantastic. And vector fields. Vector fields already require some experience with university analysis. The third secret example is graphs. Graphs also form a Lie algebra, and that is what we discussed today, and that is what we shall use tomorrow when we discuss Poisson brackets and deformations of Poisson brackets. The theory which I present now, you can use it in courses like group theory for second-year bachelor students in mathematics and physics, or as supplementary chapters in combinatorial methods in physics. The topic which I'm telling now, which I review now, it was created 30 plus, maybe 32 years ago by Maxim Kontsevich. Actually, in the context of mirror symmetry. In mirror symmetry, as it was designed in 92, 93, it didn't work. But it worked much later in a completely different domain, in a completely different world of deformations of Poisson brackets, of Poisson structures. So today we have 45 minutes and 45 minutes. In the first 45 minutes, we discuss the algebra of graphs. And in the second part, we discuss the Lie algebra of graphs, the differential graded Lie algebra of graphs, homology and the usefulness of graph homology for mathematical physics. So we begin. We study graphs. Please let us understand. We study finite graphs. We study not empty graphs. We study graphs with edges. And everything will be filtered by the big rating. How many vertices, how many edges. And the idea is, when I say a graph, I shall actually mean a larger combinatorial topological structure. I shall mean a graph in which somebody, maybe you, somehow ordered the edges. Let this edge be first, let this edge be second, let this edge be third, let this edge be last. So graphs for us will be a pair, just a topological incidence, which vertex is incident to which vertex along an edge, and the ordering of edges.
Total ordering. Total ordering.
Just in the meantime, let us have one first, second, 1, 2, 3. Somehow we shall then say external.
Excuse me,
Yes.
I have checked. Now you can write normally, not reverse. It's right itself.
Thank you very much. Okay. So who worked in the topic? The topic was created in 92-93 by Kontsevich. Then in 96-97, relation of this topic to Poisson geometry, graphs, Poisson geometry, was understood again by Kontsevich. Then for 15 years, nothing happened. Then there appeared Willwacher Felder from Zurich, who made a substantial contribution. Tonight we shall probably end. We shall conclude with that statement of that contribution. What I am now talking about is naturally related to quantum groups and to everything discussed by Drinfeld. And then my team, we joined the topic around the year 2015-2016. And that evolved into my talk tomorrow about deformations of Poisson structures. So we assume, just for beauty, for simplicity of your introductory exercise, that every graph that we studied is connected. We can even assume that our graphs have no bottlenecks. You skip out a vertex and the graph does not split into two. So they are in that respect strongly connected. They are not empty for reasons of convenience. There are no one cycles. There is no edge with ending at the same vertex. And for reasons which you will understand in 5 minutes, there are no multiple edges. So if there are two vertices, they may be connected at most by one edge, but not by many.
So one vertex is strongly connected.
One vertex, we shall study graphs consisting of at least two vertices. Just at the very bottom, there is the exclusion zone.
Sometimes it is important to have extreme cases.
We are not extremists. So, okay. So we study such graphs, and edges today are not directed. It is precisely the transition from today to tomorrow, when every edge becomes an arrow, which allows doing some differential calculus. That we shall discuss today by the end, and tomorrow in the beginning of it. No multiple edges, no one surface. And we see today over real numbers. So all vector spaces are real vector spaces. We take a vector space of graphs with real coefficients. Just a huge vector space. Of course, it is stratified by components with that many vertices and that many edges. And by default, we shall always sit in an homogeneous component with a suitable number of edges. So you see that a graph for me now is an object which consists of a graph of that many times one graph in usual perception, plus that many times another non-isomorphic graph, plus you may have finite sums, because in a given vertex edge grading, you have only finitely many topologically non-isomorphic graphs. it doesn't mean that we start taking disjoint unions. Here is a graph, here is a graph. We take formal sums.
But do you identify some graphs, yeah, in this sum, or so I mean some isomorphic classes?
Isomorphic, we shall now count as one graph.
But if the ordering is changed, that's linearly independent.
We are now passing to your question precisely which effectively space, how big is the basis up to isomorphism. That is precisely what we are going to discuss. So for every component of our formal sum, for every graph in usual understanding, we take an ordering of edges. Some edge is called first, some edge is called second, and so on. So somehow it is given for this specific graph. We consider not only the topological structure, the graph, but we postulate the wedge ordering. It means with one and the same graph, it effectively means that if we reverse, if we swap the order of two edges, now second goes in front of the first. We get a minus sign. So every time we swap two edges in the wedge product, we get a minus sign in the front of the entire graph. So that was with our graph. It topologically stays the same. The ordering of vertices changes. The ordering of vertices changes. We get a minus. Just a second.
Excuse me, what do you mean by isomorphism classes of graphs? Two graphs with different orderings are not isomorphic?
Two graphs with different ordering. Suppose they are isomorphic topologically.
Yeah.
Now we have a question of comparing. Are they equal to each other or are they minus equal to each other?
Okay.
We have a graph and an ordering of edges. We have a graph which is topologically the same and an ordering of edges. We must learn how to compare these graphs. And we do it like this. Suppose, without loss of generality, that here the edges are somehow enumerated 1, 2, 3, last. And suppose, without loss of generality, that the ordering is 1, 2, 3, 4, 5. So you know that topologically, this graph is indistinguishable from this graph. Vertices go to vertices, edges go to edges. You know which vertex goes to which vertex, which edge, therefore goes to which edge. Therefore, you can take the ordering of edges in the image, how it was prescribed by somebody, it was a given datum, and you can express every edge in that ordering through your canonical 1, 2, 3, and so on last. You get a wedge product of edges. Some edge in our initial reference times some edge, times some edge, times some edge. Compare it with our original ordering, 1, 2, 3, 4. If it is obtained by a parity even permutation, the two objects are equal. If not just isomorphic, but equal. If the permutation is odd sign, then they are minus each other. A very natural idea. So indeed, when you compare some echelon standard graph number 1 and topologically isomorphic number 2, then not just the topological isomorphism, but the quality is taken by the permutation which acts on the set of edges. Here it is. So, for example, when we consider these graphs, you immediately recognize that topologically it is one and the same. The handle allows you to identify what goes elsewhere. So you see that the edge opposing the handle here it is last, it has index 4, and here it is before last. So to get one ordering from the other, you must switch 3 and 4. So the graphs are minus equal to each.
I think you can also consider subgraphs and use the number of reversals, yeah?
Both yes and no. Both yes and no. For instance, yeah, one of the sufficient properties which you effectively inspect is that you have an automorphism of our graph, which swaps, interchanges an odd number of pairs of edges. Odd number of pairs, and you automatically get an image. Example. This graph has an automorphism which swaps 2 and 4. Edge number 1 goes to edge number 1, edge number 3 goes to edge number 3, and these two vertices are flipped. They go to each other. So we see, irrespective of all the calculation in our previous example, that our graph is isomorphic to a graph where one pair of edges is interchanged. So the graph we suddenly discover is equal to minus itself.
Yeah, because 3 cycles are even, yeah.
3 cycles have 2 types of automorphism. One cyclic symmetry, and you know nothing because the cyclic permutation of 3 objects
Both are even.
Cyclic permutation of 3 objects is even, but a flip, when one edge stays the same and one pair is flipped, is a parity odd permutation.
No, so this is only the cycle.
So,
Because you use transposition.
you use a transposition, it is a 2 cycle. So suddenly we see that we have a very interesting space of graphs. First of all, we take our initially given space of graphs with real coefficients, a vector space. We take its quotient by the linear equivalence relation. So this count how we can compare topologically isomorphic graphs by looking at the orderings of their edges, it gives us an equivalence relation. Well, every graph is equal to itself. If one graph is equal to another to the third, then the first is equal to the last, and it is symmetric. Linear equivalence relation means that when we have a formal sum of graphs, we can do such relabeling of vertices, relabeling of edges, change of order of edges in every graph, in every component, independently of what we do in other terms of the sum. And we suddenly see that in the quotient space of the vector space modulo this equivalence relation, we have a gigantic zero. We have a gigantic zero. It consists of graphs which are equal to minus themselves. One example of such a graph which is equal to minus itself is already in front of us. So zero can be big, and all the calculations, and now there is a big business of calculations. Why? I shall tell you later. There is a big business of calculations with such graphs. It is fairly unfeasible without a computer software. That computer software has been created in the past 10 years, partly by Thomas Willwacher and his team, partly by my collaborator Ricardo Buring. Now he is at INRIA in France, l'Institut National de Recherche en Informatique Avancée. These high-performance calculations, in particular, the graphs. As I said, we can identify zero graph easily if we have an automorphism with which interchanges edges in pairs, not in longer sets. And does it an interchange in an even number, of pairs? Let us see. There are many examples of non-zero graphs.
What you really call automorphism? This should preserve the sign or no?
No. It is purely topological. It is purely topological. Okay, so when I want to distinguish graphs, I look only at the topological structure. They are visibly different. They are not isomorphic. But when they are isomorphic, next question is: are they equal or opposite to each other? And only then I use the abstract structure of the edge order. Yes.
Is this graph in the first example strongly connected?
My pedagogical zeal obliges me to forget some of our initial assumptions made along the way. I guess no, it is not, because if in this Ursa major you skip out this vertex, it becomes disconnected. Yes, but never mind. The point is that when we talk real business, then they are just by themselves strongly connected, and everybody is happy.
So we will have the vector space freely generated by strongly connected graphs up to isomorphism, and then we also
then we take a quotient over the linear equivalence relation. Yes, you are right. So there still exist non-zero graphs. For instance, this one. Even when we do business and when we talk strongly connected graphs in the context of Poisson geometry, we shall use this edge, this stick many times. This graph, which will be extremely important for us, it is not strongly connected. Okay, it is zero. It is zero because it is equal to minus itself for an obvious physiological reason. Suppose that we know this graph as an incidence table. Vertex 1 is incident to vertex 2, vertex 2 is incident to vertex 3. Vertex 1 is not incident to vertex 3. And the ordering of edges is lexicographic. Edge 1, 2 is first, and edge 2, 3 is second. And then we have two realizations of our incidence between vertices. This is vertex 1, this is vertex 2, this is vertex 3. Or on the very same picture, this is vertex 3, this is vertex 2, and this is vertex 1.
But you enumerate vertices.
Nothing will in the end, in comparison, nothing depends on labeling of vertices. Everything depends only on the ordering of edges. So suddenly we see that a graph with ordering of edges first and second is isomorphic to the graph with ordering of edges first and second here. So it is equal to minus itself. Indeed, there is an automorphism of the graph as a topological structure, which acts by a parity odd permutation on the space of edges. So it is zero. And we discussed that this constellation, this graph, is also zero. It is equal to minus itself because it admits a symmetry which swaps which flips two of its edges. We see by Janusz that this graph is also zero. We don't yet notice it if we try a cyclic rotation. Because the cyclic permutation of three objects is a parity even permutation. But if we flip our graph, then one edge remains itself and two edges are interchanged. So we get an overall minus sign, the graph is equal to minus itself. And so on. So we do have that zero. It is rather big of graphs which are equal to minus themselves. We must neglect them. And one of the claims which I shall produce is that all of the calculus which will reappear is well-defined modulo zero graphs. If you do whatever reasonable with a zero graph, it will not contribute to the final result. This is why we discarded multiple edges. We postulated it from the very beginning because we knew where to go. Every graph with a multiple edge, with a double edge, obviously has a symmetry which interposes these two edges and does nothing else to the rest of the graph. Of course, such graphs will be equal to minus themselves, therefore zero. And let us talk lemma, provisional lemma for the future. Such a rectangle. Why is it zero as well? Well, it admits a flip. Up goes down, down goes up. Two edges go to themselves, and upper edge and lower edge are interchanged. One pair. Let us now consider wheels. Wheels is an important word. We shall use it in what follows. So a wheel is a regular n-gon, a central axis point, and many spikes from the axis to the vertices on the wheel, on the periphery. We understand this is a four-wheel. It has four sides, the center, and four spikes. Claim. Every even-sided wheel is a zero graph.
Is it a simple procedure to check whether this is zero or not?
Run over, it is an NP hard problem. You run over, you calculate the automorphism group of your graph. You start running over the non-trivial elements of your automorphism group. You inspect how they act. So it is
no elementary.
Even odd number of pairs which go one to another. It was a sufficient condition which in practice very often helps you check if an odd number of pairs are interchanged, then you get nothing else happens. Then you get a zero. So good exercise is to show that even-sided wheels are zero graphs. In contrast with the case of odd-sided wheels, which are not zero graphs, and that is important. We shall see odd-sided wheels in what follows. They will be good for algebraic number theory. Okay, so we are introducing.
Sorry.
We are now working from now on with the vector space of graphs with ordered wedge ordering of edges. Modulo the linear equivalence relation when we act by permutation on the set of edges, we get the minus sign of the permutation. So this is the space of graphs in the literature now, in the advances, in the annals graph, and we shall consider the cases when the number of vertices is given, when the number of edges is given. We shall study homogeneous components, and nothing depends on the labeling of vertices. Just we take invariance of the permutation group acting on vertices. It is just the relabelings. It doesn't matter. We study topological structures with extra datum, the wedge ordering. People, why was it designed a long time ago, 30, 35 years ago? Apart from it is all very natural. Several remarks. How exactly it appeared in the context of homological mirror symmetry, I don't know. I don't remember. What the use of it was understood between the years 92 and 96. We study in differential calculus, I mean at large, analysis on manifolds. We study many structures, differential geometric structures, such as brackets. Poisson brackets understood poetically. For instance, the Schouten bracket, the anti-bracket in theoretical physics. In Batalin, in BV, in Batalin-Vilkovsky formulas, they are bilinear operations with certain anti-symmetry acting on two arguments. We have already seen something of the kind. An operation relating two arguments in a prescribed way with certain anti-symmetry. Graphs, as topological combinatorial structures, are a way, one of the many possible ways to extend the theory of brackets to collective effects, to collective polylinear operations acting on many arguments. Instead of two arguments of a bracket, we can have many arguments involved in the construction of a new object. So graphs are a natural way to extend our calculus where initially we had brackets of two objects, like Poisson bracket or BV anti-bracket.
You can also view the bracket as a, say, cohomology operator. Yeah, so isn't it more convenient for?
Actually, the two ideas are merged. You guessed it right. You guessed it right. For us to conclude this part of theory, let us have some preparatory information. Let us have more examples of zero graphs. I just tell you in advance that these examples are zeros. When you start studying this domain of science in the context of quantum groups, Poisson geometry, Poisson homology, these graphs, secretly I tell you, show up almost at once. Why? I tell you tonight and tomorrow. Why is this graph obtained from the tetrahedron? Why is it zero? Well, you know, in a blacksmith shop, there is a device to pump air into the furnace, like this. It is made of some steel and leather. It has one side, it has another side, and it is contrasted. Now assume, because we are abstract people in theoretical physics and in mathematics, that the two triangular sides, the upper and lower, can pass through each other, not feeling each other. You interchange up and down. So that the upper side becomes lower side and the lower side becomes upper side.
Didn't you say that with odd number of?
Yes, yes, yes.
So this is particular example.
This is a particular example of it because this edge is swapped with this edge is swapped with this edge, and this edge is swapped with this edge. So three pairs of edges are interchanged.
But it's not a wheel, is it?
It is not a wheel. The tetrahedron is a wheel. You would agree that it is a wheel. But I think that this graph has not three vertices, not four vertices, but five vertices. It has not 6 edges, but 7 edges. It does not fit to be a wheel. Also, in a wheel, we have no vertices of altitude. We have no vertices with two neighbors in a wheel, and here we do. So it is not a wheel. No. No. I appreciate your question. We shall soon understand that all of these graphs are obtained from wheels by taking some graph differential. I promised you a differential graded Lie algebra. So they are obtained somehow. You know, several years ago, I supervised a student about whom I saw for the first time what it means to be a geometer. There are people with algebra abilities and with geometry abilities. People with algebra abilities think with the left hemisphere of the brain, and people with geometry abilities think with the right hemisphere of the brain. So there were many discussions where I was extremely impressed. There was a picture of a graph, or even a table of incidence relations between vertices. There was a picture of a graph or a table of incidence relations between vertices. My student, she came, she looked at the tables or she looked at the two pictures for 7 seconds. And then she said, you know, these graphs are isomorphic. The following 20 minutes were spent on explaining why these graphs are isomorphic under a certain permutation of however labeled vertices and therefore given edges. Let us take these two vertices and let us take this vertex out of the picture, preserving all the incidence relations. Well, indeed, you get a perfectly symmetric image. And about this perfectly symmetric image, it takes only a few seconds to understand it is a zero graph. Because it is really symmetric with respect to the vertical line, and you can easily find the flip which interchanges an odd number of pairs of vertices. And why it is called the monkey? Well, provisionally, we remember Leonardo da Vinci's human, and this monkey is like this. You see, the monkey touches the floor with the right palm and lifts the right leg into the air. It is like this. Okay, and this graph also is zero for immediate considerations of symmetry. Let us see it as an exercise. 1 pair, 2 pairs, 3 pairs, 4 pairs, 5 pairs of edges go to each other under a flip, under a symmetric. Okay. We have understood that we study graphs, topological combinatorial structures, we only postulate the wedge ordering of edges. We get a linear, we study the vector space of graphs, spanned by graphs. We get homogeneous components with that many vertices, that many finitely many edges. We introduce the linear equivalence relation by looking at the ordering of edges. And we get a huge zero. Okay, we tolerate a huge zero. And we do the calculations on the closure. We understand that it is an interesting thing to detect zero or non-zero graphs. We look at the combinatorial properties of symmetry. We have accumulated some examples that we shall use in what follows. 2 remarks. Everything that I tell you, we shall use in the second hour when we discuss the Lie algebra structure. Okay, 3 remarks. Remark number 2. Graphs generalize the concept of binary alterations. So the simplest graph relates an object to an object by an edge, a stick. Relates an object to an object by an edge, how they interact. And larger graphs allow us to create polylinear, multi-argument, somehow anti-symmetric or skew-symmetric operations on the spaces of, in particular, multi-vectors. Brackets, Poisson brackets, in particular, multi-vectors on manifolds. Lastly, in the past 20 years, there appeared competing variants of graph complexes where it is not edges which are odd, but vertices which are odd. So there are 2 competing sciences. They have different domains of applications in geometries, in Poisson geometry, in symplectic geometry, in generalizations. They allow us to describe different analytic effects, different analytic constructions.
But aren't they dual in a sense?
In the extreme bottom, we have incidental isomorphisms. If you go a little bit higher, nothing in common. Sometimes there are results by, I never remember the exact attribution. Maybe something is done by Felder and Willwacher in Zurich. Something is maybe done by Dolgushev in Boston or somewhere. That cohomology of one complex somehow constrain the cohomology of another. So if you know for different degrading components cohomology here, then in the other complex, cohomology must lie somewhere in between. It cannot be smaller than this one, it cannot be bigger than this one. There are very deep abstract results about how these 2 worlds with odd edges and odd vertices interact between each other. A priori, almost not anywhere. They are really different worlds. And there are some results about what can be seen here by knowing something there. That is a very deep question. It is rather fresh. Maybe there were results 7 years ago, 8 years ago. I think we heard a talk in Drinfeld in 18. One of the talks was touching this material. And by the way, the 2 complexes heard something about each other through, it was by Anton Alexeyev. In the talk of Anton Alexeyev, I think he touched in Drinfeld 18, he touched the question, does anything here know about anything there? The answer is yes, but in a very strange way and not always. Okay, after the break, we shall I don't remember in which order. First of all, we shall study the algebra of graphs, how we can multiply graph by a graph, non-commutative, non-associative multiplication. Then we shall introduce a blow-up, a vertex blow-up differential. There are many differentials, even in our system. We shall study the Lie algebra of graphs. We shall study the differential Lie algebra of graphs. We shall study the graph complex, and we shall discover its relation to quantum groups. We shall discover its relation to Poisson geometry and to many other very to number theory, to algebraic arithmetic numbers. Here it is. I think we run out of time.
So now we have a break of 15 minutes, or maybe a little bit less. We meet again at 3:15 Warsaw time. Tu kliknąć i tu kliknąć.
Okay, we may resume. Please.
We are ready?
Yes.
Yes, we are ready. We can restart.
Ten nagrywanie wystartowało.
Yes, it is recording. It's in progress again.
Okay. So, thank you. We resume. In the first hour, we understood that we studied finite graphs. So far, we only looked at the space of which particular finite graphs, finitely many, whatever ordering of edges, or on the sets of edges. Many graphs are non-zero, some graphs are zero. Everything is filtered by the vertex edge D grid. Now let us see what we can do if we have one linear combination of graphs and another linear combination of graphs. Let us make them into algebra. Let us understand how we can multiply graphs. First, let us assume that we have a graph gamma 1, graph gamma 2, and our favorite vertex in the victim graph gamma 2. How do we define the insertion of gamma 1 of the entire graph? Everything is done by linearity. If our graph gamma 1 is a linear combination of something, then of course we proceed by linearity over those somethings into a given vertex V of gamma 2. Namely, how to insert a graph into a vertex of somebody else. We take a vertex, it was in gamma 2, probably incident to something in the rest of gamma 2. We replace the vertex V in gamma 2 by the entire graph gamma 1. And the adjacent edges from the rest of gamma 2 initially coming to this vertex, they are attached to vertices in gamma 1, which we insert in all possible ways. So this edge now goes here, 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 here. We take a formal sum. Another edge from the rest of gamma 2 initially coming to this vertex V. It also goes via the Leibniz rule over all of the vertices of gamma 1 inserted. And still another edge, independently from all that was previously said, attaches to vertices of gamma 1. So every edge initially incident to a vertex V now runs over all of the vertices in the graph gamma 1. It is precisely this construction which Merkulov explained in Drinfeld in 2018. That is why he introduced graphs in a very strange way with half edges. And then it was discussed how some half of edge is connected to the other half of edge. So such attachment of external edges in gamma 2 to vertices now provided by gamma 1 goes completely independently edge with respect to any other edge. And we sum all the possible variants. So when we introduce a sufficiently big graph into a vertex initially with sufficiently many neighbors, the resulting sum can be colossal. Of course, you need
Some with coefficient 1.
some with everybody is counted with coefficient 1, and we get many terms counted with multiplicity 1. They are new graphs with edges. We study graphs with wedge ordering of edges. We postulate that in every term in that formal sum, the edge ordering, the edge ordering is initially there are graphs from what we inserted, and then the old edges of the old victim graph. Notice that when we insert a graph into a vertex, we lose one vertex, but we don't lose any edges. As many edges we had, so many edges we have. With gamma 1, morally, nothing happens at all. Simply new edges are attached to gamma 1 from externally, but they are old edges in gamma 2. We saw them connected to the vertex B in our graph. Of course, here, very unfortunately, in the literature, Merkulov, Dolgushev, Anton Alexeyev, Felder, Willwacher, Kontsevich, there are two schools. One school first takes the edges of the graph which we inserted. The other school takes first the edges into which we inserted. But this is, of course, up to a sign, one and the same science, one and the same thing. So far, we inserted the entire of gamma 1, maybe by linearity, if gamma 1 was something plus something plus something, into our favorite vertex of gamma 2. Usually in graphs, we don't have favorite vertex. Therefore, the insertion of a graph gamma 1 into gamma 2 is the insertion of gamma 1 into every vertex of gamma 2. Every such insertion provides a formal sum of graphs with multiplicities 1 and this edge ordering. And now we insert gamma 1 into this vertex of gamma 2, into this vertex of gamma 2, into that vertex of gamma 2, into everything. This operation is very strange. That it is not commutative, it is just entirely obvious, because it has no moral reason to be commutative. You get physiologically very different graphs when you insert gamma 1 into gamma 2, and when you insert in the entire gamma 2 in a vertex of gamma 1. You get completely.
But then some of them can be 0, yeah?
Yeah, some incidentally can be 0. And the most interesting thing is to ask what happens if you insert whatever into a 0 graph, or when you insert a 0 graph into whatever.
So actually you can use either rational numbers instead of reals, or
Yes.
just integers.
Yes, you can use integers. You can. Yes. More interestingly, our operation is also not associative.
Then you will get ring, yeah?
It is not associative for a very simple physiological reason. When you insert something into something, then the two objects forever become nearby, because they are incident through some edges. But when you insert, first you insert graph number 2 into graph number 3, and then into the resulting object, you start inserting graph number 1, then it can very easily happen that in 3, you insert graph number 2 somewhere here and graph number 1 somewhere here, and they are very far away from each other. So when you insert graph number 1 into graph number 2, and then this combination into graph number 3, 1 and 2 are always near each other.
This slightly resembles Gersten-Haber product.
It is basically two descriptions of the same mega science. Yes, 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 yes. It is precisely the transitional lecture from today to tomorrow, which I don't read, but references are. Yes. It is precisely encoding endomorphisms of the spaces of linear operators by using graphs. It is Gersten-Haber theory.
Ideological in this.
Yes, and Murray Gersten-Haber was just delighted with all this reinterpretation. Okay, so we have such an operation. We already have the algebra. Let us see for clarity how it works. Suppose that we have a stick and a stick. We insert stick 1 into stick prime. So stick 1 is inserted into this vertex, and stick 1 is inserted into the other vertex. We have this picture and we have this picture. And now we have 4 options when this edge attaches to this vertex, or attaches to this vertex, or attaches to this vertex, or attaches to that vertex. We take everything with multiplicity unit, and because we get 4 times one and the same thing, we get 4 times such an interesting graph with the ordering of edges prescribed a long time ago. First goes the only edge here, and second, lastly, goes the only edge here. Likewise, an exercise, when we insert a stick into the 3-wheel the tetrahedron, then we blow up this vertex, or we blow up this vertex, or we blow up this vertex, or this vertex into the stick. And in the resulting graph, whatever edges were incident to this vertex, we somehow let them attach to the ends, to the vertices of the inserted stick. Maybe all of the 3 come to one end. Maybe all of the 3 come to the other end. Maybe 2 arrive here and 1 arrives here. So when they all come to one end of the stick, we get a picture with the coefficient calculated yourself. When we blow up a vertex and distribute, distribute 2 to one edge to one end and 2 edges to the other end, calculate the coefficient. Well, here I mean that there is some ordering on the space of edges given by our formula. Here there is an ordering on the space of edges given by our formula. You blew up different vertices, you get different pictures, collect similar terms. It is doable. It is possible on a piece of paper to calculate all of the, to study all of the situations and to collect similar terms with sign.
But there is one delicate point here. Do you consider automorphism which map one summand to the other, or not?
No. First we write what we obtained, and only then we start.
But then, if I remember well, this double interval is 0. Yeah?
This guy is 0.
No.
Yes.
You say I prime is 0, yeah, or not?
This graph is 0, yes.
Yeah.
This
So you
graph
get 0. Yeah.
you get here in this example, you get 0.
Okay.
Yes.
So formally, this insertion of graph gamma 1 into vertex of the other graph works like that we take a single vertex, we split it, we disconnect this graph in this vertex, and then we may connect this these 3 edges that to anything we want. Yes, we have to take all combinations.
All combinations possible.
Okay, thank
Yes.
you. So there is no abstraction. We can place any graph in any vertex of any other graph. Okay.
So this graph is not strongly connected. We should forget about this.
Yes, forget about that. That strong connectedness assumption was done by Willwacher. We shall see it in 20 minutes. That if initially objects were strongly connected, then after some perturbations, they will also remain strongly connected, so that whenever you want to solve some equations upon graphs, you are safe enough to seek inside the subspace of strongly connected.
But here the product does not.
Yes, here it does not apply. Here just forget. Very stupid of me to having announced it something this. Yes. So we inserted one graph into a vertex of another graph. We inserted one graph into another. We had two. We had two graphs. So now take two graphs for typographical reasons. Let us call them A and B. Formally speaking, A is a linear combination of graphs. B is a linear combination of graphs. Everything is done by B linearity. The bracket. The postulate. The bracket of two graphs, A and B, is the insertion of R into vertices of B minus the insertion of B into vertices of R. With an extra sign, so that we, formally speaking, obtain not a bracket, but a super bracket. Every graph has its own grading. The grading is the number of edges. So all our spaces of graphs, all our homogeneous components are graded by the number of Z grading by the number of edges.
No, but because they are linear combinations, so you sum up all over.
You proceed by linearity in R, you proceed by linearity in B. You sum. So if you look at this sign, then we notice that in both the terms, in the minuend and in the subtrahend, the wedge ordering of edges is first go the edges of R and last go the edges of B. Because here they go in the exact opposite order, and then we permute all of the edges of B with all of the edges of R. So the edge ordering of all the terms here and here is first go edges of R, then go edges of B. It is the same as inserting R into B and B into R, but preserving the RB edge order. And we do everything bilinearly over sums of graphs in R and in B. You now see that our bracket is graded skew. Our bracket is graded skew, and moreover, a non-trivial fact completely doable by second-year students who study group theory or general algebra in such compulsory courses, or I don't know, symmetry in physics, group actions in physics. Jacobi identity, graded Jacobi identity, holds perfectly. This is our favorite shape of the Jacobi identity, which says that we have two adjoint actions, one by R and one by B, with the sign which takes into account that R and B are graded objects. The commutator of two adjoint actions by R and by B minus by B and by R equals the adjoint action by the bracket of R.
This is a graded commutator.
Yes, it is just the usual. The graded commutator of adjoint actions is the adjoint action by the graded commutator.
But you write dgLa, so what is differential?
It will be. It is here. Don't you see? Okay. So
You're saying this is very easy, but it's not so obvious, right? If the product with the circle was associative in the beginning, this would be immediate. But
there is no contradiction in what you say. It is easy, but not obvious. Yes. The idea is there is a magnificent paper published precisely by that student who thinks geometrically, who sees a picture and in a few seconds understands the answer. This is a paper with all the justification proofs which were taken for granted by Maxim Kontsevich, which were taken for granted by Felder Willwacher in Zurich, which were taken for granted by Merkulov and by Dolgushev in the East Coast. This paper is a collection of exercises, is very good for you if you want to kill any student at an oral exam in combinatorics or in group theory or in general algebra. All solutions are completely transparent. It takes between minutes and days to get the idea of accurately tracking the orbits of group actions, groups of automorphisms, which make a zero graph into a zero graph, which act on a zero graph and give you minus the original graph. My claim is that on the space graph, on the quotient space, modulo the linear equivalence relation we introduced 1 hour ago, the Lie super bracket is well defined. The Jacobi identity holds at the level of vector space, not modulo zero graphs, but it is really an equality. It really is some linear combination of graphs truly equals at the level of vector space to another combination, not modulo zeros. So the Jacobi identity holds and all the properties, you take a bracket with a zero graph, it is a zero graph. Because everything which is non-zero comes out, accumulates with a zero coefficient plus a linear combination of zero graphs. This is a wonderful text in its algebraic group theoretic transparency. We make minimal assumptions. We look at those group actions. We count, as Janusz says, only with integer coefficients. And we sometimes, at all times, pay attention to who comes with plus, who comes with minus, due to the edge orderings. It was an intuitive discovery of Kontsevich in '93, around the year 93-94, that everything of this takes place. Then it was generalized, then there were alternatives with vertices odd, edges even, and so on. But now we get the Lie superalgebra of graphs. Jacobi identity holds perfect. Jacobi identity, by the way, is much easier to justify than the well-defined ones. The Jacobi identity really is the graded commutator of adjoint actions is the adjoint action by the graded commutator. And here you really have the physiology, immediate cancellation when R goes in gamma somewhere here, when beta goes in gamma somewhere there, you immediately see the cancellation. And what remains is precisely what you need in the right-hand side of the Jacobi identity.
So this version of the Jacobi identity is much better in general because it works also in the case of non-skew symmetric brackets.
Yes. Yes.
But the people sometimes prefer cyclic permutation, which is nonsense in this.
Janusz, golden words. Moreover, there is a class of non-commutative geometries which are not Alan-Kohn non-commutative geometries, but which are the so-called Kontsevich non-commutative symplectic supergeometries. In brief, in plain words, it is this. Let us ask a question. How much of graded commutativity do we need to build all of the analysis which we, as mathematical physicists, study in the first 3 years of bachelor? That is up to differential forms, vector fields, multi-vector fields, calculus on manifolds, differential calculus on manifolds. We discovered, initially, it was Maxim Kontsevich 92, the International Congress of Mathematics. And then it was developed by me in 2012, so 20 years later. Only cyclic invariance is needed. You don't need to know what happens when you have a necklace, when you have gems on the necklace. You may not swap 2 consecutive gems on a necklace. But on a piece of rope, you can shift the gems cyclically through some marked infinity code. And then you get some sign if your gems are themselves graded with a certain grade. And that assumption of what you know when you do cyclic permutations allows you, regardless of any non-existent graded commutativity, allows you to build all of the multi-vector calculus, even variational, for KdV structures, for KdV equations for integrable hierarchies. And there, when you do the Lie superalgebra of multi-vectors, it is precisely this type of Jacobi identity which you prove regardless of any commutativity. So what we have in textbooks, it is usually proved by swapping plus minus signs neighbors. The proof is much more basic. It works not because of that. You can prove the very same result by much weaker assumptions. And it is precisely this shape, not cyclic permutation, but precisely this. The commutator of a joint is the adjoint of commutator. It is precisely this. Okay. So we have a Lie algebra. And we suddenly notice that we had our stick, which, as Jan teaches us, denies all assumptions of strong connectedness. Okay. The stick can be inserted into a graph to effectively blow up every vertex consecutively into an edge. By the way, even in our setup today, you can have many other differentials on this space of graphs. For instance, you may have edge contracting differential. When you take every edge consecutively and collapse it into a vertex, you will have a completely different theory. Claim Kontsevich and Felder and Anton Alexeyev and Sergei Merkulov teach us homology will be the same.
According to the Jacobi identity, this should mean that product stick with itself is 0.
Yeah? Stick with itself is 0, and it is precisely the graph which we saw 1 hour ago and which we flipped. It is precisely that. It is precisely that. So a theorem, once again, is that the square of the differential vanishes. And it is vanishing really hardcore at the level of vector space of graphs, not modulo 0 graphs, but really you get in that vector space. Apart from the 0 was very big, there was really the 0, namely 0 coefficient times whatever graph plus 0 coefficient times whatever graph plus 0 coefficient times whatever graph. There was the genuine 0, and here you really get the gene.
Stick is homological vector. Yeah?
Yes. The stick, yes, the stick is the Richardson mean phase bracket with the Scouten bracket. In your Gerstenhaber world. Okay.
So may I ask, so maybe I'm a bit confused because you're saying that this relation calls upstairs, but earlier you computed actually the product of the stick with itself, and it was 4 times the double stick, which is a 0 graph. So, so that would already explain why b squared is 0 after taking the quotient.
This is Jacobi identity applied to stick. Stick is 0.
Yeah, but you computed earlier the double stick is
0.
in the quotient space.
Yeah.
But this is in the quotient space, but the claim is that this is real 0,
It is
not in the quotient, but up there.
Okay. Let us return back to our Jacobi identity. Here is our Jacobi identity. In the left-hand side, R and B are the same. In the left-hand side, R and B are the same.
This is d squared.
This is the left-hand side of our Jacobi identity is precisely this. What do we get in the right-hand side? The Jacobi identity promises that to whatever victim of d squared, by the Jacobi identity, we apply the bracket of stick with the stick. And the bracket of stick with the stick is 0 is a 0 graph. Because vertex, edge, vertex, edge, vertex. 0 graph. So in the Lie algebra, we apply to whatever victim a 0 graph. And Nina Rutten promises us that the result would be a 0 graph in the so after taking the quotient, it will be 0. Now, but it can be very big. The promise is that upstairs it is 0 times whatever.
It should be also remarked that this minus something is the same as ABC, so we get 2 times ABC.
Yes, the left-hand side actually doubles. Nobody dies in the left-hand side. The left-hand side actually doubles. Okay. Several tiny remarks before we make philosophical conclusions. Everything is perfectly well defined, and everything is somehow by God tuned for effective calculations. If your graphs initially were not particularly ugly, then after whatever Lie algebraic operations, they will remain not particularly ugly. Okay, the differential of 0 graph is 0. So we have a differential graded Lie algebra. Everything is well defined. If in the original graph there were no leaves, that is vertices of valency 1. You remember the handle of that frying pan. So if you did not have that, that is strongly connected example of graphs, then we shall have no leaves in the resulting graphs. Formally, for people, formally they appear. Actually, they disappear. They all cancel out. Good exercise. Thirdly,
formally it means without this quotient, yes?
No. Formally, I mean, Janusz teaches us whenever you have to act by a graph on a graph, you write down like doctor prescribed. You write down everything that appears.
Yeah.
In the Lie bracket, you write down everything that appears minus everything that appears.
Okay, and they cancel.
And they cancel out.
Okay.
Yes. Okay. What effectively our differential, the vertex blow up differential does? It goes over vertices of the argument graph. It blows every vertex into a stick such that something does attach to the vertex and something does attach to the vertex. So we cannot, or effectively, we do not form leaves. So when everything is attached to one side of the stick, and nothing except the stick itself is attached to the other vertex. Formally speaking, we did make such graphs, but they all canceled out. So really, we have partitions of a non-empty set of edges coming to one end of the stick and non-empty set of edges coming to the other end of the stick. And there is a handshake lemma. It is used everywhere in practical calculations. If we have no transitional vertices with only one edge here and only one edge here, so every vertex has valency at least 3. Then whatever you do after the application of the differential, however gamma be complicated, you will not have transitional vertices. That is, all the resulting vertices still will have a valency at least 3 or higher. Okay, so effectively, it was very difficult to read the seminal papers by Kontsevich and therefore by Willwacher in the Annals and in the Inventiones, because they assume this understood in passing, and they blow up effectively only vertices of valency 3 or higher, because all the vertices with valency 2 will cancel. Okay, so this is a chain of exercises that help you kill any student at the oral exam in group theory or general algebra. Let us remember it, it is extremely practical and convenient. And now, miraculous thing. Just let me conclude my talk with several examples and several mega claims. So we have a differential graded Lie algebra acting on a space with many homogeneous graded components, vertex edge degraded. Our vertex blow up differential increases the number of edges by 1. It takes a vertex and blows it up. And it therefore increases the number of vertices by 1, because it took a vertex and made it into 2 vertices. So it moves us diagonally into the next component, this one with. We may ask, we have a differential. What do we know? What can we say about cohomology of the graph complex with respect to this vertex blow-up differential? Amazingly, almost nothing is known, and amazingly, we can say, we are interested in graph cocycles. Running a little bit ahead, I can tell you, there is a fascinating paper by Willwacher Zhivkovich. Zhivkovich then went to Luxembourg to Merkulov. We can, by calculating Betti numbers, we can calculate the dimension of graph cohomology up to vertex edge degrading up to 30. You probably, my dear colleagues, you probably do not feel how fast the number of graphs grows. It is, roughly speaking, n to the power 2n on n vertices. When those graphs are interesting to us, some more. It is really super exponential. The number of generators of graph cohomology, that is, of linearly independent generators, graph cocycles, in 3030, it is 17 decimal digits. The miracle is that we can calculate the number of generators without knowing a single generator. That was the result. There is some generating function. That was the result of Willwacher and Zhivkovich from 2014. Amazing. Let us ask about.
Is it something now about how the size of this cohomology grows with by degree? Also as fast as the number of graphs.
But it remains totally unclear in the limit of infinitely many vertex edges. Does it make a zero proportion of all graphs in that gradient, or a finite fraction? Does it grow, or does it asymptotically decrease? A problem for a PhD thesis. Because of tomorrow, for reasons of tomorrow, we are interested in graphs, in graph cocycles in the degradient n to n minus 2. It is precisely those graphs which will help us to deform Poisson brackets. Because of that Gerstenhaber business behind everything. Let us have any example. The first example was known to Maxim Kontsevich initially in the Ascona paper from '96. It is the tetrahedron, or it is the wheel with three sides. Its differential is zero. Its differential is count yourselves how many our graph we discussed it. Then in four wheel is nothing, and in that degrading where the four wheel sits, there is nothing. No non-trivial cocycles. We take cohomology modulo coboundaries. In the five wheel class, we do have one generator. It is the five wheel, the Chrysler plus the roof or the prism with one direction. It is a very instructive exercise. To rediscover this graph and to understand why its differential is expressed in terms of Leonardo da Vinci's human, which cancels out monkey, and the stone graph, which we saw in our previous example 1 hour ago. Then in six wheel class, there is nothing. I'm in the corner of a table of Willwacher Zhivkovich with very low vertex edge gradient. Gamma 5 is in front of us. Gamma 7 is also a non-trivial class. We calculated it here sort of for the first time. Something, a different representative of that class, was known to Willwacher before us, but he knew only a huge representative, and we provided a code. Then, gamma 3, gamma 5, gamma 7. Who is next? Next is the bracket of gamma 3, gamma 5, non-trivial cocycle, then gamma 9, and then so on. Willwacher shows in a fundamental paper in Inventiones, Willwacher shows that for whatever odd number of sides, 3, 5, 7, there will be a non-trivial cocycle in the graph complex by Kontsevich. At least one, maybe more in that degrading, but at least one will exist. And you can take their commutators. You freely generate a differential gradient Lie algebra by these iterated commutators of the wheels. Fundamental miracle. You get the Lie algebra, which was known in mathematics as the Lie algebra of the Grothendieck-Teichmüller Lie group, introduced by Drinfeld in 1890 in the context of quantum algebras. And that group, that Lie group, is known to be the Galois group of the algebraic completion of rationals, modulo rationals. That is, all rational numbers stay the same and all imaginary units are somehow mixed between each other. You take the Lie group, that Galois set up, and its Lie algebra is precisely what is generated by these graph cocycles. So we have our arithmetic number theory. We have the graph complex here. We have quantum groups by Drinfeld, and it is only 2012 by Francis Brown in Oxford who recognized the Galois group here.
So you say this is truly algebra in this case, yeah?
Yes.
It's not graded.
Infinite dimensional.
Infinite dimensional.
Yeah.
Infinitely generated, infinite dimensional Lie algebra, which shows up in Galois theory of rationals, which shows up in quantum groups by Drinfeld, which shows up in the proper grading cohomology of the Kontsevich graph complex, and which shows up in deformations of Poisson structures. Tomorrow, we shall try to merge some of these seemingly different fields. It is actually one and the same science. The transitional fact is a very non-trivial explanation how, by taking graph cocycles, you get multi-vector fields on the spaces of multivectors. In one phrase, it is very simple. We put multivectors into vertices of our graphs. I promised you n-ary operations, multilinear operations, which are bigger than the stick, than binary operations. And every edge becomes a derivation. Every edge becomes a derivation in two possible ways, like this Houghton bracket. And that was the generalization of the Houghton bracket or differential calculus on manifolds created by Kontsevich. Brackets are generalized into multilinear operations. A natural class of multilinear operations is given by graph cocycles in the Kontsevich graph complex. And it is precisely these graph cocycles which give us well-defined deformations of Poisson structures. And that is what we should discuss tomorrow. How to deform Poisson brackets in such a way that they stay Poisson by using these graph cocycles. Here it is.
I'm not sure if we have time for questions because there is the next seminar is waiting, but I don't know, one short comment.
You spoke about cocycles, so what about cohomology? For instance, gamma 3 is cohomologically 0?
No. It is a non-trivial cocycle. When I say cocycles, I mean different cocycles.
So these are not trivial.
No. None of these guys is ever trivial. Gamma 9 has been obtained 1 year ago by Ricardo Buring. It contains only 13,000 graphs. Beyond it, nobody has never seen nothing. It is already task for supercomputers. Nobody ever saw graphs beyond.
Are there some known explicit relations between because there is this sequence gamma 5?
The arithmetic of coefficients of graphs is a completely open problem. Just which graphs to take with non-zero coefficients to form a suitable cocycle, completely unknown. There is no
this sequence gamma 3, gamma 5, gamma 7, and
they all start with a wheel plus a tail, and that tail is not known.
I'm afraid we have to go with
Yes,
this.
we have to take those questions to the
This
more.
is outside. I'm very sorry I have to tell this all. However, we meet again in a week.
If you want to.